Hello there, and welcome to The Sleepy Scientist. I'm glad you've chosen to spend a little time drifting off with me tonight. Whether you're tucked into bed, curled up on the couch, or simply letting your thoughts float through the stars, you're in the right place. Tonight we're going to take a slow, gentle journey through the history of telescopes, those quiet, curious instruments that have helped us peer farther into the cosmos than our eyes ever could on their own. From ancient stargazers tracking the dance of planets with nothing more than their eyes, to modern marvels drifting in space and reading the universe in invisible wavelengths, telescopes are the calm, patient observers of the night sky. Now, I do hope this video isn't too interesting. After all, the idea here is to help you fall asleep. But if it happens to keep your brain quietly alert for a little while, just think of it as bonus learning, wrapped in a lullaby of science. Before we begin, if you enjoy these calm and curious explorations, it would mean a lot if you gently tapped that like button and subscribed. It helps more sleepy minds find their way here. I'd also love to know where in the world you're listening from and what time it is by you, whether it's just after sunset or well past midnight. Feel free to let me know in the comments. Now, take a deep breath. Let your body relax. Let your thoughts become soft around the edges. We're about to gaze upward, slowly and quietly, at the tools that let us touch the stars from the comfort of Earth. And just before we begin, a gentle reminder. This video is for relaxation and educational purposes only, and is not intended to provide any medical or sleep-related advice. Long before lenses and glass and mirrors, before telescopes and observatories and radio dishes the size of football fields, there were eyes, just eyes, and a night sky full of questions. For most of human history, people didn't look at the stars to understand physics. They looked up to survive, to tell stories, to track time, and to feel a sense of order in a world that often didn't offer much. Imagine the sky as the original calendar, compass, and movie screen all rolled into one. In the absence of electricity or city lights, the heavens were impossibly vast and brilliantly clear. The stars rose and set with rhythmic precision, and to ancient sky watchers, they seemed to hold secrets too important to ignore. Some of the earliest astronomers weren't cloaked in lab coats or peering through telescopes. They were farmers, priests, builders, and travellers. In what is now England, over 4,000 years ago, humans constructed Stonehenge. Massive stones, hauled and arranged with stunning precision, form alignments that mark the movements of the sun. On the summer solstice, the sunrise cuts directly through the heart of the structure. Was it a calendar? A sacred temple? Maybe both. But it was undeniably a celestial instrument, created without a single lens or line of code. Travel further east to ancient Mesopotamia, in the fertile lands between the Tigris and Euphrates rivers, and you'll find some of the earliest known records of astronomical observations. The Babylonians, as early as 2,000 years before the Common Era, were charting the positions of planets and stars. They kept meticulous records, scrawled in cuneiform on clay tablets, of lunar eclipses, planetary conjunctions, and the movements of Venus. They even developed a lunar calendar and could predict eclipses. No telescope required. Just patience, observation, and a very clear view of the sky. In ancient Egypt, the sky was more than just a tool for tracking time. It was a divine map. The goddess Nut painted across tomb ceilings, arched her body over the earth, and represented the heavens themselves. Egyptian temples were often built in alignment with celestial events. The great temple of Amun at Karnak, for example, aligns with the rising sun during the winter solstice. Light would stream down its main axis, illuminating the inner sanctum in a brief and sacred glow. This was not coincidence. It was cosmic architecture. Astronomy and mythology were woven tightly together in many ancient cultures. For the Mayans of Central America, the sky was a living manuscript of gods and cycles. They tracked Venus with extraordinary accuracy, associating its movements with omens, war, and agriculture. Their calendar systems were so advanced that they could predict solar eclipses and the movements of celestial bodies centuries in advance. One of their most famous achievements, the long count calendar, marked vast cosmic cycles spanning over 5,000 years. The city of Chichen Itza even features a pyramid, the Temple of Kukulkan, designed to cast a serpent-shaped shadow during the spring and autumn equinoxes, a play of light and stone orchestrated by the stars. These early skywatchers weren't guessing. They were observing, recording, calculating. Their understanding wasn't based on modern science, but it was deeply empirical. They noticed when stars rose earlier or later, when the moon changed shape, when constellations crept across the sky from season to season. The patterns were memorized and passed down, folded into stories, rituals, and monuments. The heavens became a language, one that required no telescope to read, just a clear sky and a little patience. What's remarkable is how consistent the stars have been through all these millennia. The same constellations that guided Polynesian navigators across the Pacific Ocean guided camel caravans through the Arabian desert and told Norse sailors when to set sail from Scandinavia. Whether you were on a mountain, in a jungle, or on a frozen steppe, the sky was your map. Even the Greeks, though they came later, leaned heavily on the work of these earlier civilizations. Thinkers like Ptolemy and Hipparchus built upon Babylonian star charts to develop models of planetary motion. Hipparchus in particular made one of the earliest known star catalogues and even discovered the precession of the equinoxes, a subtle wobble in Earth's axis that causes the positions of stars to shift, slowly over time. No high-tech tools, just careful observation over years, even decades. Of course, without magnification, there was a limit to what could be seen. The planets visible to the naked eye, Mercury, Venus, Mars, Jupiter, and Saturn, were known and named. But beyond that, the deeper universe remained out of reach. The Milky Way was just a fuzzy band across the sky, its true nature a mystery. Nebulae appeared as faint smudges, if they were noticed at all. What looked like stars were actually entire galaxies, hiding in plain sight, waiting for glass and mirrors to reveal their true scale. Still, even without seeing far, our ancestors saw deeply. They saw the rhythm of time, the repetition of the seasons, the dance of shadows and light. Their observations helped them plant crops, honor deities, and mark the passage of days in ways that gave structure to life. It's no wonder that the heavens were often seen as the realm of gods. They were vast, unchanging, and just out of reach, both beautiful and terrifying in equal measure. Today it's easy to forget how dark the world once was at night, but in those times, before the hum of cities and the haze of artificial lights, the night sky was a spectacle. A dome of stars so bright and thick that it felt like you could scoop them up with your hands. That celestial theatre inspired myths, guided migrations, and launched humanity's first questions about our place in the cosmos. Even now, there's something comforting in knowing that the stars you see are the same ones seen by an Egyptian architect, a Babylonian scribe, or a Mayan priest 1,000 years ago. Their eyes and ours, separated by centuries but united by curiosity, looked up at the same sky and wondered, and sometimes that wonder was enough. Long before telescopes became the cosmic marvels we know today, there was something far more humble and earthy: glass. Just melted sand, really, heated, shaped, and cooled into shimmering transparency. But this simple material would go on to change how humans saw the world, literally and figuratively. The story of optics is a slow unfolding, a quiet revolution that began long before anyone realized just how far a curved piece of glass could take us. At first, people didn't know what to make of lenses. They were curiosities, sometimes used in jewelry or decoration. But even in ancient times, there were glimmers of their potential. The so-called Nimrud lens, found in modern-day Iraq and dating back over 2,000 years, may have been used as a magnifying glass, or perhaps it was simply decorative. Its exact purpose remains unclear, but its very existence hints that humans were beginning to notice that glass could do something unusual with light. It wasn't until the Islamic Golden Age, around the 8th to the 13th century, that optics truly began to take shape as a science. In the bustling libraries and observatories of Baghdad, Cairo, and Cordoba, scholars began to explore how light worked. Among them was Ibn al-Haytham, known in the West as Al-Hazan. A thinker of rare brilliance, he wrote a monumental book called the Book of Optics in the 11th century. Al-Hazan didn't just speculate, he experimented. He studied how light travels in straight lines, how it reflects off surfaces, and crucially, how it bends when passing through different materials, a phenomenon known as refraction. He understood that our eyes receive light, rather than sending it out, which might seem obvious now, but was hotly debated at the time. He even conducted early experiments with lenses and camera obscuras, essentially building the foundation for everything that would come after. And all of this was accomplished without modern lab equipment, just keen observation, thoughtful reasoning, and a whole lot of curiosity. As Al-Hazan's ideas spread, they mingled with discoveries from other cultures. The knowledge moved westward into medieval Europe, and slowly found its way into the hands of monks, scholars, and craftsmen. By the 13th century, magnifying glasses were becoming common tools. Reading stones, semi-spherical lenses placed over text, were used to help aging eyes make sense of cramped manuscripts. It was an age when books were copied by hand and candles flickered more than they glowed, so a little optical assistance went a long way. Then came eyeglasses. The earliest known spectacles appeared in Italy in the late 13th century. They weren't sleek or stylish. Imagine riveted leather, metal loops, and clunky glass, but they were revolutionary. Finally, people with farsightedness could read again. Craftsmen could return to fine work. It was a small miracle, one that spread rapidly across Europe. Monasteries, universities, and cities all embraced this new clarity. But despite these advances, lenses were still largely confined to helping people see better up close. No one had quite imagined turning them skyward. That would come later. For now, the growing understanding of how to shape, polish, and combine lenses laid a quiet but essential groundwork. As glass-making techniques improved, especially in Venice and the surrounding regions, so did the quality of lenses. The Venetians, famous for their glass blowing, discovered ways to create clearer, more consistent glass. This mattered a great deal because bubbles and imperfections in the glass could distort light. Smooth, clean lenses meant sharper images, and sharper images opened the door to more precise tools. Meanwhile, the Renaissance was beginning to stir. Human curiosity was bursting at the seams. Artists studied anatomy, engineers sketched machines that flapped and flew, and mathematicians explored the invisible scaffolding beneath nature. Within this energetic soup of invention and rediscovery, optics continued to evolve. In the late 16th century, spectacle makers in the Netherlands and Italy began tinkering with combinations of lenses. If a single lens could magnify, what might happen if two were used together? What if a convex lens and a concave lens were placed in just the right alignment? Some early attempts produced comically blurry results. Think looking through two fish bowls glued together. But with persistence, the image sharpened. These experiments were often driven by curiosity more than scientific rigor. Still, by the very end of the 16th century, there were reports of rudimentary spyglasses being sold at markets. These were modest tools, offering only a few times magnification, but even that was enough to excite the imagination. A faraway tower brought a little closer, a ship on the horizon just a bit clearer. It didn't take long for someone to look beyond the ships and towers and wonder about the stars. Underlying all of this, of course, was the quiet power of refraction. Refraction is what happens when light passes from one medium into another, like from air into glass, and bends in the process. The amount and direction of the bend depend on the shape of the glass and its curvature. A convex lens, thicker in the middle than at the edges, bends light inward and can make objects appear larger. A concave lens, thinner in the center, spreads light out. Learning to harness and combine these effects took time, patience, and a fair bit of trial and error. But gradually, these optical oddities became tools of transformation. They didn't just help people read or sew, they began to extend the human eye beyond its natural limit. Though no one quite knew it yet, the pieces were in place for a revolution. Glass, that simple fusion of sand and fire, had become something magical, a transparent bridge between the world we can touch and the one just out of reach. It's easy to take for granted how strange and wonderful it is that bending light through curved glass can reveal details invisible to the naked eye. That something as ordinary as a pair of reading glasses shares a lineage with the great observatories and space telescopes of today. But that's the beauty of optics. It began with the need to see a little more clearly, and ended up reshaping how we understand the universe. From dusty scrolls in Baghdad to candlelit workshops in Venice, from monks squinting at parchment to merchants marveling at ships in the distance, the story of lenses is full of quiet ingenuity, a tale of light bent and guided step by step toward the stars. In the early 17th century, a man named Galileo Galilei picked up a modest little spyglass and, with a few adjustments, pointed it at the night sky. What he saw would rattle the very bones of the universe, at least as far as people understood it at the time. Up until then, the sky had largely been treated with the kind of reverence reserved for tidy furniture. Everything was in its place. Earth at the center, stars stuck neatly to celestial spheres, the planets doing polite little dances around us. It was a cosmic snow globe, stable, ordered, and entirely Earth-centric. Galileo was not the first to use a telescope-like device, but he was the first to truly aim it upward with scientific purpose. The basic design had emerged a year earlier in the Netherlands, where spectacle makers were experimenting with combinations of lenses to magnify distant objects, handy for spotting ships, or, in less relaxing contexts, enemy movements. When Galileo caught wind of this device, he immediately recognized its potential. He didn't invent the telescope, but he refined it with startling speed. His early versions magnified objects about 8 times. Within months, he improved that to over 20 times magnification, remarkable for a homemade instrument using simple materials. Once the instrument was sharp enough, Galileo turned it skyward, and that's when the real excitement began. The moon, that familiar glowing disk in the sky, revealed itself to be a world of jagged peaks and shadowed valleys. To most people at the time, the moon was a smooth, perfect sphere, heavenly in the most literal sense. But Galileo's spyglass showed something very different. A battered, cratered surface, not unlike Earth's mountainous terrain. The moon, it turned out, wasn't flawless. It was rocky, uneven, and distinctly terrestrial. A shocking idea, given that the heavens were supposed to be pure and unchanging. Then came Jupiter. In January of the year 1610, Galileo spotted what he initially thought were tiny stars near the planet. But over several nights, he noticed something odd. They moved. Not randomly, but in a consistent pattern. Eventually, he realized these points of light were orbiting Jupiter. 4 of them. These were the moons we now call the Galilean satellites: Io, Europa, Ganymede, and Callisto. This discovery was monumental. Not everything orbited Earth. In fact, here was a clear example of a mini-planetary system in motion, around something else entirely. For supporters of the Earth-centered universe, this was a bit awkward, like finding a houseplant on Mars and still insisting Earth was the only place with life. Galileo's observations provided visible, undeniable proof that the universe was more complex than previously thought. But wait, there's more. Galileo also observed Venus, and what he saw didn't fit the old models. Venus displayed phases, much like the moon, waxing and waning shapes that only made sense if Venus was orbiting the Sun, not Earth. This lined up perfectly with the heliocentric model proposed decades earlier by Nicholas Copernicus, which placed the Sun at the center of the solar system. Until now, that idea had been more theory than proof. Galileo's observations made it increasingly hard to ignore. To put it mildly, this was not a popular take with everyone. In particular, the Catholic Church, which had long endorsed the geocentric model, was less than thrilled. Galileo's evidence undermined centuries of theological and philosophical tradition. The heavens were no longer a crystal sphere of divine perfection. They were messy, dynamic, and shockingly Earth-like. Now, it's worth pausing to mention that Galileo wasn't exactly known for his subtlety. He had a sharp tongue, and a habit of naming his discoveries in ways that didn't always win friends. When he discovered the moons of Jupiter, He named them Medicean stars to curry favour with the powerful Medici family in Florence. A clever political move, sure, but one that also made him a bit of a target. Galileo also had a flair for drama. He published his findings with flair and urgency, keen to win credit before others could catch up. His Starry Messenger, published in 1610, was part scientific treatise, part cosmic mic drop. It announced to the world that the heavens were not what we thought, and he had the drawings to prove it. One of the more humorous episodes in this saga involved Saturn. When Galileo pointed his telescope at the ringed planet, he was baffled. His telescope wasn't powerful enough to show the rings clearly, so he described Saturn as having ears or handles. He thought perhaps it was a planet with two companions glued to its side. Not quite accurate, but considering the tools he was working with, it wasn't a bad guess. It's easy to forget now just how revolutionary all of this was. Today, we accept that Earth is a planet orbiting a star, itself one of billions in a galaxy filled with other suns and worlds. But in Galileo's time, this was heresy dressed up as optics. He wasn't just rearranging planets, he was challenging humanity's place in the universe. If Earth wasn't the center of everything, what else might we be wrong about? Of course, not everyone reacted with fury or fear. Many were simply amazed. Galileo's telescope became an object of fascination. He demonstrated it to nobles and scholars across Europe, showing them the craters on the moon and the moons around Jupiter. Seeing really was believing. His discoveries spread quickly, sparking a surge of interest in telescopes, astronomy, and the structure of the universe. By the late 16-teens, Galileo's star had both risen and darkened. He was celebrated and vilified in equal measure. In 1633, under increasing pressure from the church, he was placed under house arrest, where he would spend the remainder of his life. But even then, his mind kept working. He continued to write, to study, and to push against the edges of what was known. There's a legend, probably apocryphal, that after being forced to recant his views on the motion of the Earth, Galileo muttered under his breath, "And yet it moves." Whether he said it or not doesn't really matter. The phrase captures his spirit, persistent, curious, unyielding in the face of orthodoxy. In the end, Galileo didn't just look through a telescope. He looked past centuries of assumption and dared to believe what he saw. His spyglass turned the heavens from an unreachable ideal into a landscape full of motion, texture, and surprises. It was the first true astronomical instrument, and in the hands of a stubborn Italian with a flair for mischief, it cracked open the universe. When you hear the name Isaac Newton, your mind might go straight to apples falling from trees and the laws of motion that still govern roller coasters and space stations alike. But Newton wasn't just a theorist in a powdered wig. He was also a problem solver who got his hands dirty with mirrors, metals, and more than a few optical headaches. One of those headaches involved an annoying little issue called chromatic aberration. Chromatic aberration sounds fancy, but it's really just a colourful nuisance. When white light passes through a lens, the different colours bend by different amounts because each wavelength has its own little personality. Blue light bends more sharply than red, which means they don't quite focus at the same point. The result? Blurry, rainbow-edged images that make distant stars look like they've been painted by someone with a leaky watercolour set. This was a real problem for early refracting telescopes. As astronomers tried to make their lenses bigger and more powerful, the chromatic mess only got worse. No matter how precisely they ground the glass, the colours just wouldn't behave. And bigger lenses came with other challenges too. They were heavy, fragile, and notoriously difficult to polish into a perfect shape. The longer the telescope, the worse these problems became. Some instruments ended up stretching dozens of feet long just to reduce distortion. Impressive, but not exactly easy to carry around for some casual stargazing. Enter Newton. Already deep into his work on optics and light, he realized that the root of the problem wasn't faulty craftsmanship. It was the lens itself. Instead of continuing the fight with ever more refined glass, Newton took a different approach entirely. What if, he wondered, you could skip the lens altogether? The answer lay in mirrors. Unlike lenses, mirrors don't split light into colors. When light bounces off a mirrored surface, all wavelengths reflect together, preserving the shape and clarity of the image without those pesky rainbows. This idea wasn't entirely new. Some thinkers had toyed with it before, but Newton was the first to make it work in practice. In the year 1668, he built the first functional reflecting telescope. It was a compact, elegant little device with a concave primary mirror made of a special metal alloy called speculum, which could be polished to a high shine. Light would enter the open end of the telescope, bounce off the curved mirror at the bottom, and then reflect onto a smaller flat mirror that directed the light to an eyepiece on the side. This clever arrangement eliminated the need for a long tube and a giant glass lens. It also produced clearer images, free from chromatic distortion. The resulting telescope was shorter, lighter, and far easier to use than its refracting cousins. It was a practical, elegant solution born out of deep understanding and, let's be honest, a healthy dislike for blurry rainbows. Newton's reflector telescope was a quiet triumph. When he presented it to the Royal Society, it was met with genuine amazement. Here was a new kind of instrument that sidestepped the limitations of lenses entirely, and it wasn't just a prototype, it worked. It showed crisp, detailed views of the moon and planets, despite its relatively small size. One of the reasons mirrors were so effective was their shape. Newton's primary mirror was parabolic, meaning it had a curved surface that focused incoming parallel light rays to a single point. This eliminated a problem called spherical aberration, where light from the edges of a lens or mirror focuses at a different spot than light from the center. Combining this with the elimination of chromatic aberration, Newton's design produced images that were sharp and clean, a major upgrade from the refractors of the day. Now, working with mirrors wasn't all sunshine and starlight. Speculum metal, while highly reflective, tarnished easily. That meant the mirrors had to be repolished regularly, which was a bit like trying to keep a silver spoon spotless while living in a fog machine. But even with this drawback, the advantages of Newton's design were hard to ignore. Over time, his ideas caught on. Other astronomers began building reflectors of their own, and the design continued to evolve. By the 18th and 19th centuries, large reflecting telescopes had become the instruments of choice for serious stargazing. They could be made bigger without suffering from chromatic aberration, and they allowed astronomers to peer deeper into the night than ever before. Newton's work with mirrors also highlighted something beautiful about science. Sometimes, the best way forward is sideways. Instead of wrestling endlessly with a problem, he changed the shape of the problem itself. Rather than correcting chromatic aberration, he simply designed it out of the system. That kind of thinking is what makes science not just powerful, but elegant. What's especially remarkable is how durable this idea turned out to be. To this day, the world's most powerful telescopes, whether perched on mountain peaks or floating in space, still rely on Newton's basic insight. They use curved mirrors to gather and focus light, taking advantage of the same physics that guided Newton's hands over 300 years ago. The Newtonian telescope, as it came to be known, isn't just a clever workaround. It's a testament to human ingenuity, the idea that clarity doesn't always come from pressing forward, but sometimes from turning the problem on its head and reflecting quite literally on other possibilities. So while Newton is rightly remembered for calculus, gravity, and the laws of motion, his contribution to telescopes was no less groundbreaking. With a single curved mirror, he helped clear the cosmic fog, sharpened our view of the heavens, and made it possible to see farther and clearer than ever before. All from a workshop, a bit of metal, and a refusal to accept blurry rainbows as the final word on starlight. By the 18th century, telescopes had already proven themselves to be more than just clever optical toys. Thanks to Galileo, Newton, and others, the telescope had become a proper scientific instrument, capable of revealing mountains on the moon, moons around distant planets, and orbits that didn't have Earth at the center of everything. But for some astronomers, clearer images weren't enough. They wanted more light, more magnification, more size. If a little telescope could do so much, imagine what a giant one might uncover. Enter William Herschel, a man with an ear for music and an eye for the stars. Originally from Germany and trained as a musician, Herschel moved to England and developed a fascination with astronomy that quickly turned into obsession. Not content with store-bought instruments, he started building his own telescopes, grinding, polishing, and assembling them in his workshop with the help of his sister Caroline, who had become an accomplished astronomer in her own right. Herschel's telescopes were monsters for their time. His most famous, completed in 1789, had a primary mirror over 4 feet in diameter and a tube 40 feet long. At the time, it was the largest telescope in the world. It was so big, in fact, that using it required climbing up ladders and navigating a wooden scaffold that looked more like a pirate ship rigging than a scientific tool. But the results were worth the balancing act. With his enormous reflector, Herschel did what few others had dared to do. He surveyed the entire sky, cataloguing thousands of stars, clusters, and nebulae. He discovered Uranus, the first planet found since ancient times, and initially named it Georgium Sidus, or George's Star, in honor of King George III. The name didn't stick, but the discovery certainly did. Suddenly, the solar system was bigger than anyone had thought. Herschel also observed faint, fuzzy patches of light that didn't resolve into stars, no matter how large his telescope was. These were nebulae, mysterious cloud-like shapes scattered across the sky. Some looked round and gentle, others elongated or oddly structured. He speculated that they might be collections of stars so distant that they blurred together into misty shapes. It was a radical idea, and one that would only grow more compelling as telescopes continued to expand in size and ambition. Following in Herschel's rather lengthy footsteps, a number of astronomers took up the challenge of building even bigger telescopes. In the early 19th century, Scottish astronomer Thomas James Henderson and others made careful observations of star positions, but for truly mind-bending instruments, the spotlight would soon fall on an Irish aristocrat with a penchant for oversized science. That man was William Parsons, the 3rd Earl of Ross. In the 1840s, he constructed what would become known as the Leviathan of Parsonstown. With a mirror 6 feet across, yes, 6 feet, and a tube nearly 60 feet long, it was the largest telescope the world had ever seen. Even today, it remains one of the most awe-inspiring pieces of astronomical engineering from the pre-industrial age. The Leviathan wasn't just big for show. Its size allowed it to collect much more light than any previous telescope, making faint objects visible for the first time. Through its eye, Ross observed nebulae in stunning detail. One of them, the Whirlpool Nebula in the constellation Canes Venatici, revealed a distinct spiral structure. For the first time, someone had seen the spiraling arms of what we now know to be galaxies. At the time, however, the term galaxy was still mostly reserved for the Milky Way. No one was quite sure what these spiral shapes were. Were they part of our own galaxy, just distant clouds of gas and dust? Or were they entire island universes, self-contained star systems like our own, floating far beyond the Milky Way? This was one of the great astronomical debates of the 19th century, and the answer wouldn't be settled until the following century. But thanks to Ross's enormous telescope, the question could finally be asked with some visual evidence. While the Leviathan was undeniably impressive, it wasn't exactly easy to use. The massive tube was mounted between 2 stone walls, and moving it was a challenge that involved counterweights, ropes, and a fair bit of muscle. Observations were limited by the telescope's fixed north-south orientation, and the notoriously damp Irish weather didn't always cooperate. Still, when the skies cleared, the Leviathan provided glimpses of cosmic structure that had never been seen before. As the 19th century wore on, astronomers around the world continued building bigger and better telescopes. In America, the refracting telescopes were a resurgence, with massive lenses replacing mirrors in some designs. The Yerkes Observatory, completed in the 1890s, boasted a refractor with a 40-inch lens, the largest ever successfully used in an astronomical telescope. Unlike mirrors, lenses didn't require constant polishing, but they came with their own limitations, including the return of chromatic aberration and the sheer difficulty of supporting such heavy glass without it sagging under its own weight. This era of astronomical arms races was about more than just size. It was about ambition. Every new telescope represented a leap into the unknown, a wager that, if we could just see a little further, we might unravel the universe's secrets, and in many ways that gamble paid off. Star clusters became clearer. Nebulae took shape. The night sky stopped being a simple scatter of lights and began to look like a structure, layered, complex, and filled with vast, faint mysteries. And in the midst of this growth, something else was changing: the role of the astronomer. No longer just an isolated thinker peering through a personal instrument, the astronomer had become part of a larger scientific network. Observatories were established. Star catalogues expanded. Teams of assistants tracked, measured, and recorded. Astronomy was growing up, and the telescope was its tool of choice. The giant glass age was both a literal and metaphorical expansion of our cosmic vision. With each bigger mirror and longer tube, humanity reached a bit further into the night. And while we still didn't know exactly what those spiral shapes were or how far away they stretched, we were starting to ask the right questions. We were beginning to understand that the sky wasn't just a ceiling, it was a doorway. And the bigger the glass, the wider that doorway became. As telescopes got bigger and better, astronomers started running into a frustrating truth. No matter how finely ground your mirrors or how wide your lens is, if you're looking through the bottom few miles of Earth's atmosphere, things are going to get a little blurry. The air above us is always shifting, rippling with temperature changes, filled with moisture and shimmering with turbulence. This makes stars twinkle, which is lovely if you're writing poetry, but less helpful if you're trying to take precise measurements of a galaxy 100 million light-years away. This atmospheric distortion, known more formally as astronomical seeing, is one of the biggest challenges for earthbound telescopes. It's like trying to read a street sign at the bottom of a swimming pool. The light gets through, but it's wavy, jiggly, and sometimes downright mischievous. Add in other obstacles like clouds, humidity, dust, and the ever-creeping glow of artificial lights, and it's clear that placing a telescope just anywhere won't do. Location matters a lot. That's why, in the 20th century, astronomers started chasing altitude. The higher you go, the less atmosphere you have to peer through. Up there, above the haze and heat of cities and valleys, the air is thinner, drier, and more stable. It's cooler too, which helps sensitive instruments stay calm and collected. And with fewer people around, you're less likely to find yourself fighting off light pollution from street lamps or the sudden glow of a shopping centre. One of the earliest and most ambitious efforts to rise above it all came in the late 19th century with the creation of the Lick Observatory, perched atop Mount Hamilton in California. Completed in the 1880s, it was the first major observatory built on a mountain, nearly 4,000 feet above sea level. Transporting materials to the summit required building a winding road and hauling everything up by horse and wagon. It was a logistical nightmare and a scientific triumph. Once finished, the observatory housed the world's largest refracting telescope at the time, and it offered a clearer view of the stars than almost anywhere else on Earth. That success set the stage for a new era of mountaintop observatories. In the early to mid-20th century, astronomers kept climbing higher, leading to the construction of the Mount Wilson Observatory near Los Angeles. It became the site of groundbreaking work by Edwin Hubble and others, who used its powerful telescopes to measure galaxies and uncover the expansion of the universe. From this perch above the smog and lights of Los Angeles, astronomers quite literally changed our understanding of the cosmos. But even Mount Wilson had its limits. As cities expanded and air quality declined, astronomers looked for even more remote and pristine locations. The next great leap came with the Palomar Observatory, also in California, completed in the 1940s. Its 100-inch Hale telescope was a marvel of engineering, representing the pinnacle of mid-century astronomy. To cast its giant mirror, engineers used a revolutionary technique involving a glassy material called Pyrex, the same stuff found in your kitchen measuring cups. The mirror took nearly a year to cool down after casting, and several more years to grind and polish to perfection. At Palomar, astronomers gained a powerful new eye on the universe, but as always, science continued to crave clearer, darker skies. This led to one of the most ambitious observatory sites on Earth, the Mauna Kea Observatories in Hawaii. Rising nearly 14,000 feet above sea level, the summit of Mauna Kea is among the best places on the planet for astronomical observations. The air is dry and still, the skies are dark, and the atmosphere is thinner than nearly anywhere else accessible by road. Building on Mauna Kea wasn't easy, and it came with significant cultural and environmental challenges. The mountain is sacred to many native Hawaiians, and its development has sparked important conversations about the intersection of science and indigenous rights. These are complex and ongoing discussions that continue to shape how observatories are planned and built. Scientifically, though, the site is extraordinary. Telescopes on Mauna Kea have produced some of the clearest ground-based images of the night sky ever taken. With instruments like the Keck Observatory, featuring not one but two 10-meter mirrors, astronomers can study distant galaxies, track asteroids, and peer into the early universe. The high elevation reduces atmospheric distortion dramatically, allowing these telescopes to compete with even some space-based instruments. While building observatories on mountaintops helped solve many problems, it didn't eliminate them entirely. Even at high altitudes, the atmosphere still shifts and wobbles. To counteract this, modern observatories use a technique called adaptive optics. It sounds like something out of science fiction, but it's surprisingly practical. Lasers are fired into the sky to create artificial guide stars, and mirrors inside the telescope flex and adjust in real time, sometimes hundreds of times per second, to cancel out the blurring effects of the atmosphere. The result? Images so crisp you'd swear they were taken from orbit. Another growing concern for ground-based astronomy is light pollution. As cities expand and LED lighting becomes more widespread, it's getting harder and harder to find dark skies. Even a small amount of sky glow can drown out faint stars and galaxies. This has led to new efforts to preserve dark sky areas and rethink how we light our streets and buildings at night. Some observatories have even worked with local governments to implement lighting ordinances that protect the night sky. Despite these challenges, the pursuit of perfect clarity continues. Observatories are now being built in places like the Chilean Andes, where the Atacama Desert provides some of the driest, clearest air on Earth. And future observatories will push even further, using new materials, larger mirrors, and increasingly sophisticated software to capture the cosmos in ever greater detail. In the end, every observatory is a monument to human patience and ingenuity. These mountaintop sentinels remind us that even when the world below is noisy and chaotic, there are quiet places above where the stars still speak clearly. If we're willing to climb high enough, build carefully and listen. In the world of astronomy, clarity is everything. For centuries, we've tried to get clearer views of the universe by building bigger telescopes, polishing better mirrors, and climbing higher up mountains. But no matter how high you go, there's still one persistent problem: Earth's atmosphere. It's great for breathing, not so great for stargazing. The atmosphere blurs and bends starlight, distorting the view like a wobbly window pane. Even the best ground-based telescopes perched on remote mountaintops still have to peer through a swirling, shimmering cocktail of air. Astronomers had long dreamed of a solution. Take the telescope above it all into space, where there's no air to interfere, no clouds to obscure, and no city lights to wash out the stars. It sounded like science fiction for decades. Then came the Hubble Space Telescope. Launched in April of 1990 aboard the Space Shuttle Discovery, Hubble was one of the most ambitious scientific instruments ever conceived. It was a collaboration between NASA and the European Space Agency, and it had taken years to design, build, and test. Its mirror was just over 7 feet wide, small by ground-based telescope standards, but its location made it unbeatable. Orbiting about 340 miles above Earth, Hubble had an unobstructed view of the universe. No atmosphere, no twinkle, just pure, clean starlight. Expectations were sky high. Hubble was supposed to revolutionize astronomy, to show us the cosmos in unprecedented detail. But there was a small problem, actually a very precise, deeply frustrating problem. The primary mirror had been ground to the wrong shape. Not wildly wrong, just off by about 2 microns, roughly 1/50th the width of a human hair. But in the world of optics, that was enough to blur images and turn Hubble's debut into a public embarrassment. The headlines were brutal. A billion-dollar telescope with blurry vision wasn't what anyone had in mind. Some called it the Hubble Flubble. Late-night hosts had a field day. But behind the scenes, NASA scientists and engineers got to work. Fortunately, the flaw was well understood and, better yet, fixable. The solution came in the form of a corrective instrument called CoStar, a set of tiny mirrors designed to counteract the imperfection, like a pair of glasses for a nearsighted telescope. In December of 1993, astronauts aboard the Space Shuttle Endeavour performed a daring spacewalk to install the fix. It was like eye surgery, but floating in orbit, wearing a spacesuit, and with the whole world watching. The repair was a success. Hubble's vision snapped into focus, and just like that, the universe opened its front door. The images that followed were nothing short of breathtaking. Nebulae blossomed in vivid colour. Distant galaxies resolved into spirals and clusters. Supernova remnants glowed like cosmic fireworks. But the real turning point came with a quiet experiment, a bit of astronomical patience known as the Hubble Deep Field. In 1995, astronomers pointed Hubble at a seemingly empty patch of sky. It was a tiny spot about the size of a grain of sand held at arm's length, located in the constellation Ursa Major. For 10 days, Hubble stared at this blank region, collecting every photon it could. The result? Nearly 3,000 galaxies appeared in that tiny frame. Not stars, galaxies. Each one home to billions of stars. The universe, it turned out, was more crowded than anyone had imagined. The Hubble Deep Field changed everything. It gave astronomers a glimpse into the early universe, revealing galaxies that formed when the cosmos was just a fraction of its current age. It also gave the public a sense of just how vast and rich the universe really is. That tiny sliver of sky, which once seemed empty, held multitudes. It was humbling, exhilarating, and a little dizzying. Since then, Hubble has continued to deliver jaw-dropping discoveries. It helped measure the rate at which the universe is expanding, a number known as the Hubble constant. It spotted evidence of black holes at the centers of galaxies. It studied the atmospheres of exoplanets and captured dramatic views of colliding galaxies. It even took portraits of the outer planets in our own solar system, reminding us that beauty isn't reserved for distant corners of space. One of Hubble's great strengths is its versatility. It observes invisible, ultraviolet and near-infrared light, giving astronomers a broad toolkit for exploring different kinds of cosmic phenomena. It's been used by thousands of researchers around the world, often through a competitive process to win precious telescope time. The result is a telescope that's not just a single project, but a platform for decades of discovery. Part of what makes Hubble so beloved, even outside the scientific community, is its ability to capture the imagination. Its images are stunning, not just because they're scientifically valuable, but because they're beautiful. Pillars of gas reaching like fingers through space, galaxies tangled in a slow-motion gravitational dance, the delicate filigree of a star's final breath. These aren't just data, they're cosmic artwork. Hubble's longevity has been another surprise. Originally planned for a 15-year mission, it has now been in orbit for over 3 decades. Thanks to multiple servicing missions by astronauts, it's had new instruments installed, old parts replaced, and its capabilities upgraded far beyond what was initially imagined. In many ways, Hubble has aged more like a classic violin than a piece of tech, growing more valuable with time. Eventually, of course, Hubble will be retired. It's slowly drifting toward the end of its operational life, and there won't be any more shuttle missions to repair it. But its legacy is secure. Hubble proved that space-based telescopes are not just viable, they're transformative. By rising above the atmosphere, it gave us the clearest views we'd ever had and showed us that what once seemed empty sky is filled with light, history, and wonder. It also proves something more subtle but just as important, that patience, precision, and the courage to fix mistakes can lead to greatness. Hubble stumbled, got back up, and then helped redefine how we see our universe. Not bad for a telescope with glasses. Not all telescopes see. Some of them listen. They don't use mirrors or lenses, and they're not interested in starlight. Instead, they tune in to the universe's quiet hum, the low-frequency whispers of radio waves that fill the cosmos like a deep and ancient background song. This is the world of radio astronomy, where the night sky isn't just something to look at, but something to hear. The story of radio telescopes begins not with an astronomer, but with an engineer. In the 1930s, a man named Carl Jansky was working for Bell Telephone Laboratories, trying to track down sources of static that were interfering with transatlantic radio calls. He built a rotating antenna, what he called a merry-go-round, and began recording signals from different directions in the sky. Most of what he picked up was terrestrial, thunderstorms, nearby electronics, that sort of thing. But then he discovered a faint hiss that returned every 23 hours and 56 minutes, the length of a sidereal day, the time it takes for the Earth to rotate once relative to the stars. This mysterious signal was coming from the center of the Milky Way. Jansky had, quite accidentally, detected radio waves from space. At the time, few people in the astronomy world quite knew what to make of it. Jansky wasn't an astronomer, and radio technology was still in its early stages. But one man who took it seriously was Grote Robert, an amateur radio operator with a big backyard and even bigger ambition. In 1937, he built the world's first true radio telescope, a parabolic metal dish about 30 feet wide, and began systematically surveying the sky. Reber's work helped confirm that the universe was indeed broadcasting in radio. It wasn't loud, but it was there, and just like that, a new branch of astronomy was born, not by gazing upward, but by tuning in. Unlike visible light, which can be blocked by clouds, dust, and atmosphere, radio waves slip through most of these obstacles with ease. They come from some of the most energetic and exotic phenomena in the universe. Pulsars, quasars, black holes, and even the afterglow of the Big Bang itself. These signals often go unnoticed by optical telescopes, which is why radio astronomy has opened entirely new windows into the cosmos. One of the most iconic instruments in this field was the Arecibo Observatory in Puerto Rico. Built in the early 1960s, its massive dish was 1,000 feet wide and nestled into a natural limestone sinkhole. Arecibo wasn't just large, it was enormous, a giant ear pressed to the sky. Suspended above the dish was a complex receiver system that could detect faint signals from across the galaxy and beyond. Arecibo made headlines throughout its life. It helped discover the first known binary pulsar, providing evidence for gravitational waves long before they were directly detected. It studied asteroids, mapped the surfaces of planets, and even beamed a message to a distant star cluster in an attempt to say hello to any potential cosmic neighbors. That message, transmitted in 1974, included information about humanity, DNA, and our solar system. A sort of interstellar greeting card, hopeful and a little bit lonely. Sadly, Arecibo suffered structural damage and collapsed in 2020, bringing an end to its long and productive career. But its legacy lives on, not just in data but in inspiration. For many people, Arecibo wasn't just a telescope, it was a symbol of human curiosity on a grand scale. Another powerhouse in radio astronomy is the Very Large Array, or VLA, located in the New Mexico desert. Despite the understated name, the VLA is anything but ordinary. It consists of 27 individual dishes, each 82 feet wide, arranged in a giant Y shape across the plains. What makes it special is how these dishes work together. Using a technique called interferometry, the VLA combines signals from all its dishes to simulate a single telescope with an effective diameter up to 22 miles. This dramatically increases resolution, allowing astronomers to see fine details in distant galaxies, supernova remnants, and mysterious radio sources. The VLA helped identify the structure of distant quasars, quasi-stellar radio sources that shine with the energy of 1 trillion suns, and are powered by supermassive black holes at the centers of galaxies. It has traced the jets of particles shooting from these black holes, revealing dynamics invisible to the eye but blazing in the radio spectrum. And it's not just about looking outward. Radio telescopes are also used to study our own cosmic neighborhood. They track solar activity, map neutral hydrogen clouds drifting through space, and even assist with spacecraft navigation. Their ability to detect invisible phenomena makes them essential tools in the astronomer's kit. Then there's SETI, the search for extraterrestrial intelligence. For decades, radio telescopes have scanned the sky for signals that might not be natural. The idea is simple. If an advanced civilization is broadcasting, we might be able to pick up their call. It's a quiet kind of listening, one that requires patience, open-mindedness, and a lot of hope. So far, no confirmed signals have been found, but the search continues. The famous WOW signal detected in 1977 remains one of the most tantalizing mysteries. It was a sudden, strong, narrowband radio signal that stood out from the cosmic background, lasting 72 seconds before vanishing without a trace. Was it a cosmic coincidence, an earthly glitch, or something more? No one knows. But for a moment, the universe seemed to whisper something unexpected. Radio astronomy teaches us that the cosmos is not just a silent film, it's a symphony. There are frequencies all around us, filled with information that our eyes can't see. Galaxies murmur, black holes growl, and the universe itself hums with a faint microwave echo left over from its explosive birth nearly 14 billion years ago. And all of this is happening right now, all around us, day and night. While we go about our lives, making coffee, walking dogs, and brushing teeth, the universe keeps talking. We just needed the right instruments to hear it. With every new radio dish and every tuned frequency, we uncover a deeper harmony beneath the stars, a language of light beyond light, sound beyond sound. A conversation that began long before we were here, and one that, with a little luck and a lot of listening, we just might be able to join. The universe glows even in the dark, not with visible starlight or brilliant bursts of gamma rays, but with a gentler, quieter warmth. The faint glow of infrared radiation. It's the kind of light you can't see, but you can feel. If you've ever held your hand near a campfire or stood in the sunlight with your eyes closed, you've experienced it. Infrared is the language of warmth, and in astronomy, it tells us stories that visible light keeps hidden. Infrared light lies just beyond the red end of the visible spectrum. It has longer wavelengths than the light our eyes can detect, which means it can slip through things that visible light cannot, like dust, gas, and clouds. This makes it incredibly useful for studying parts of the universe that would otherwise remain cloaked and mysterious. One of the biggest challenges in observing the cosmos is that a lot of the interesting stuff happens in dusty places. When stars are born, they form inside thick clouds of gas and dust, which block visible light. Trying to observe a newborn star in visible light is like trying to spot a candle through a thick fog, but infrared light, that gets through. It pierces the clouds and reveals what's going on inside. Infrared telescopes allow astronomers to witness the formation of stars and planetary systems, the slow collapse of gas clouds, and the swirling disks of matter that may one day become solar systems. It's a view of the universe's private life, the quiet moments before the stars come out to shine. But there's a catch. Observing in the infrared isn't easy. Anything warm gives off infrared radiation, not just stars and galaxies, but also the telescope itself. A telescope at room temperature glows in infrared like a radiator in the dark. So to see the faint warmth of distant galaxies or cool planets, you need to chill your telescope, often to just a few degrees above absolute zero. It's like asking your telescope to sit perfectly still in an ice bath while listening for whispers from across the universe. That's where the Spitzer Space Telescope came in. Launched in 2003, Spitzer was designed to observe the universe in infrared from above Earth's atmosphere, which itself radiates a fair bit of infrared and tends to get in the way. By placing the telescope in space and cooling it with liquid helium, astronomers created an ideal environment for detecting faint heat signatures from across the cosmos. Spitzer wasn't the first infrared space telescope, but it was one of the most successful. It spent over 16 years observing the universe, from nearby asteroids to the farthest galaxies ever detected. It looked at the dusty disks around young stars, the cool glow of brown dwarfs, objects too massive to be planets but too small to ignite as stars. and even helped identify some of the first known exoplanets by studying the heat they gave off. One of Spitzer's most powerful contributions was in the study of star formation. In visible light, star-forming regions can look like black voids, blank spots in the sky where light simply doesn't get through. But through Spitzer's infrared eyes, those same regions are revealed as bustling nurseries, full of young stars in the earlier stages of life. It's like turning on a thermal camera in a dark room and seeing everything suddenly come alive. Spitzer also helped refine our understanding of galaxies. Many galaxies, especially the ones forming stars rapidly, are enshrouded in dust. That dust absorbs visible light and re-radiates it in the infrared. By looking at galaxies in infrared, astronomers could study their structure, star formation rates, and even the supermassive black holes lurking at their centers, all with a clarity that visible light alone couldn't provide. And then there were the exoplanets. Spitzer was one of the first telescopes to measure the infrared light coming directly from a planet outside our solar system. That may sound simple, but it's incredibly difficult. Stars are so much brighter than planets that spotting the planet's glow is like trying to see a firefly next to a floodlight. But by observing when a planet passed behind its star, a moment called secondary eclipse, astronomers could isolate the planet's infrared light and study its atmosphere. This technique led to remarkable discoveries. Spitzer found planets with temperatures hotter than lava, winds moving faster than sound, and orbits that stretched the definition of extreme. It revealed that even worlds we can't see in visible light still leave a warm signature, and that with the right instruments, we can read those signatures like heat-printed postcards from across the galaxy. Of course, even the best missions come to an end. In 2020, Spitzer was retired after running out of the coolant that had kept it so frosty and sensitive for so long. But its legacy lives on, not just in the data it collected, but in the way it changed how we think about what's visible and what isn't. Infrared astronomy reminds us that darkness is never truly empty. Even the coldest parts of the universe emit some warmth. Giant gas clouds glow softly. Rogue planets drift through space with just enough heat to be noticed. The earliest galaxies, formed billions of years ago, still send out faint ripples of infrared light, stretched and cooled by the expansion of the universe. And here we are, on a tiny planet warmed by a modest star, building instruments that can detect those whispers. It's a quiet triumph. A reminder that sometimes the best discoveries happen when we stop staring directly and start sensing more gently. When we listen not just for brightness, but for warmth. Infrared light shows us what's hidden, what's soft, what's in the process of becoming. It reveals stars not yet born, planets in their infancy, and galaxies glowing gently on the far side of time. All of it wrapped in a soft shimmer of heat, just waiting for the right kind of eyes to notice. Most of the universe is quiet, or at least it looks that way from here. Stars twinkle gently, galaxies glide across the sky, and the cosmic background hums along at a relaxed pace. But if you could see the universe in high-energy light in X-rays and gamma rays, you'd realize it's not so calm after all. It's full of explosions, collisions, and gravitational drama on a scale that makes Hollywood thrillers look tame. To observe these cosmic catastrophes, astronomers use a special kind of telescope. These aren't the kind you can perch on a mountaintop and peer through on a clear night. X-rays and gamma rays don't behave like visible light. They don't reflect off mirrors or bend through lenses in quite the same way. And worst of all, Earth's atmosphere blocks them completely. That's very good news for life on Earth, but inconvenient for astronomers, so as usual we had to go up. Meet Chandra and Fermi, two space-based observatories designed to see the violent beauty of the high-energy universe. The Chandra X-ray Observatory, launched by NASA in 1999, was named after Subrahmanyan Chandrasekhar, the Indian-American astrophysicist who studied the evolution of stars and helped explain the structure of white dwarfs. It's a telescope built for extremes. Instead of looking at stars in peaceful equilibrium, Chandra observes the aftermath of their deaths, the glowing remnants of supernovae, the furious jets of neutron stars, and the invisible grip of black holes. Because X-rays are absorbed by Earth's atmosphere, Chandra had to go high, about 85,000 miles above the planet in a highly elliptical orbit. From this lofty perch, It watches the universe at its most dramatic. One of Chandra's most iconic observations is the Crab Nebula, the remnant of a supernova that lit up the sky nearly 1,000 years ago. In visible light, it looks like a tangled web of glowing gas. But in X-rays, Chandra reveals a pulsar at the center, a spinning neutron star beaming radiation like a cosmic lighthouse, surrounded by a shock wave of energy that pulses outward in haunting, ghostly waves. Chandra also observes galaxy clusters, where entire galaxies collide and interact. These enormous structures glow in X-rays because of the hot gas trapped between them, gas heated to tens of millions of degrees. It's a cosmic soup where gravity is strong enough to contain temperatures that would vaporize almost anything we know. And then there are black holes. You can't see them directly. They swallow light and refuse to give up their secrets. But when matter spirals into a black hole, it heats up to unbelievable temperatures and emits X-rays in its final frantic moments. Chandra watches this infall of doomed gas and reveals the outlines of the invisible. It's like hearing the screams of something before it vanishes behind a curtain. While Chandra focuses on X-rays, the Fermi Gamma Ray Space Telescope looks even higher on the energy scale. Launched in 2008, Fermi studies gamma rays, the most energetic form of light in the electromagnetic spectrum. These are the shock waves of the universe. Gamma rays are produced by the most extreme events: collapsing stars, merging neutron stars, and particles accelerated to near the speed of light. Unlike Chandra, which uses specialized mirrors to gently nudge X-rays into detectors, Fermi relies on high-energy particle physics. Gamma rays can't be focused with mirrors, so Fermi uses a complex array of detectors that track the particles produced when gamma rays strike. It's not so much an eye as it is a cosmic seismograph, reading the tremors of invisible energy. Fermi has helped uncover gamma ray bursts, or GRBS, which are some of the most powerful explosions in the universe. These brief flashes of gamma rays can outshine an entire galaxy, though they usually last only a few seconds. They're thought to be caused by the collapse of massive stars or the merger of two neutron stars. Events so energetic they reshape space-time itself. Thankfully, they're incredibly far away, which is just how we like our cosmic violence. Fascinating but not close. One of Fermi's other surprises came in the form of mysterious structures extending above and below the center of our galaxy. Huge gamma-ray bubbles, each tens of thousands of light-years across. These so-called Fermi bubbles may be remnants of an ancient outburst from the supermassive black hole at the heart of the Milky Way. They're faint but massive, like bruises on the face of the galaxy left by a long-forgotten impact. High-energy astronomy doesn't just show us dramatic events, it also changes how we understand time and structure. These observations reveal processes that happen over milliseconds, or stretch across billions of years. They help us test theories of relativity, quantum mechanics, and cosmic evolution. In many ways, X-ray and gamma-ray telescopes are like time machines with anger issues, showing us the violent birth and death throes of stars, galaxies, and sometimes even space-time itself. What's remarkable is that all this mayhem is happening silently. In space, there's no air, no wind, no sound. A supernova may release more energy in a second than the sun will emit over its entire lifetime, but there's no boom. Just a burst of invisible light flung across the universe at the speed of, well, light. And if your telescope is tuned just right, you'll catch it. These instruments also remind us that the universe is complex. It's not just what we see with our eyes or through optical telescopes. There are layers of reality, some hot, some cold, some quiet, some explosively loud if space had sound, all stacked on top of each other like a cosmic sandwich. If you only look in one wavelength, you miss most of the story. X-ray and gamma-ray observatories let us peek at the raw, unfiltered side of the cosmos, the version where stars die violently, where black holes feast, and where galaxies collide like slow-motion fireworks. And yet, even in all that chaos, there's structure, beauty even, patterns in the wreckage, harmony in the destruction. It's easy to think of space as peaceful, but part of its majesty comes from the contrast. Somewhere out there, in the cold and quiet darkness, a star just exploded. A neutron star spun fast enough to tear itself into an X-ray beacon, a black hole tugged at space and light with invisible fingers, and above Earth, Chandra and Fermi are listening, watching, turning those distant, dangerous events into stories we can read. Violent, yes, but beautiful all the same. If telescopes were superheroes, the James Webb Space Telescope would be the one with the glittering cape, the golden shield, and the ability to see through time itself. It's not just another telescope. It's a marvel of engineering and ambition, decades in the making, and it's taking us further into the universe's past than we've ever gone before. And it does all this while floating in the quiet cold of deep space, wrapped in high-tech foil and golden hexagons that look like something out of a futuristic dream. Launched on Christmas Day in the year 2021, the James Webb Space Telescope, JWST for short, is the most powerful space telescope ever built. It's the long-anticipated successor to the Hubble Space Telescope, but it doesn't just build on Hubble's strengths. It shifts the entire focus, literally, by specializing in infrared light. That means it can see things that are too faint, too cold, or too far away for even Hubble to catch. Why infrared? Because the universe is expanding. As galaxies race away from us, the light they emit is stretched, like the lowering pitch of a siren as it passes. This stretching shifts the light into longer wavelengths, eventually into the infrared part of the spectrum. The farther away a galaxy is, the more its light is shifted. If we want to see the earliest galaxies, the ones that formed just a few 100 million years after the Big Bang, we need to see in infrared. And JWST is built to do exactly that. But seeing this deeply into the past requires more than just a good camera. It requires an observatory unlike anything we've ever sent into space. Let's start with the mirror. Unlike Hubble's single glass mirror, JWST's primary mirror is made up of 18 hexagonal segments coated in a thin layer of gold. Gold is excellent at reflecting infrared light, and the segmented design allows for a mirror over 21 feet wide, about 3 times larger than Hubble's. The bigger the mirror, the more light you can collect, and more light means seeing fainter, more distant objects. The mirror is so large it couldn't fit inside any existing rocket, so it had to be folded like a giant piece of scientific origami. Once in space, it slowly unfolded over several nerve-wracking weeks, a process with hundreds of potential failure points. Engineers around the world held their breath as one motor after another clicked into place, each step critical to the telescope's success. It was quite literally a game of cosmic Jenga in zero gravity. And then there's the sunshield. If JWST had a personality, the sunshield would be its anxious but utterly necessary sidekick. The telescope has to stay extremely cold, just a few dozen degrees above absolute zero, so it doesn't emit its own infrared light and swamp the signals it's trying to detect. The sunshield is about the size of a tennis court and is made of 5 ultra-thin layers of heat-resistant material, each one thinner than a human hair. It blocks heat from the sun, Earth, and Moon, keeping the telescope shaded and chilled. Positioned at a special spot in space called Lagrange Point 2, about 1 million miles from Earth, JWST orbits the Sun along with us, always staying aligned behind the Earth and its own protective sunshield. This remote location is key to keeping it cold and stable, but it also means it's far beyond the reach of repair missions. Unlike Hubble, which astronauts could service from the space shuttle, JWST had to work perfectly the first time, no pressure. Fortunately, everything unfolded just as planned, and soon JWST began sending back its first images. And what images they were! One of the first, known as Webb's first deep field, showed a galaxy cluster called SMACS 0723. The image revealed thousands of galaxies, many of them stretched into delicate arcs by the gravitational lensing effect of the cluster's mass. Some of the galaxies are so distant that their light began its journey over 13 billion years ago, before Earth even existed. The level of detail is breathtaking. Stars with diffraction spikes, galaxies so small and faint they look like smudges on a cosmic canvas, structures and shapes we've never seen before. And it's not just pretty pictures. Every image carries scientific data, revealing chemical compositions, temperatures, and motions. We're not just looking at galaxies, We're learning how they formed, how they grew, and what kinds of elements they contain. JWST has also turned its gaze closer to home, studying exoplanets with a level of precision that's never been possible before. By analysing starlight that passes through a planet's atmosphere, scientists can detect the presence of specific molecules like water vapour, methane, or carbon dioxide. These measurements are key to understanding the atmospheres of distant worlds and even searching for potential signs of life. The telescope has examined the TRAPPIST-1 system, a collection of rocky exoplanets orbiting a cool red dwarf star just 40 light-years away. Some of these planets are in the so-called habitable zone, where temperatures might allow liquid water to exist. With JWST, astronomers are beginning to look not just at the existence of planets, but at their actual weather and climate. What makes all of this even more extraordinary is the thought that we're seeing things as they were billions of years ago. When JWST looks at a distant galaxy, it's not seeing the galaxy as it is today. It's seeing light that left that galaxy when the universe was still in its infancy. It's a kind of time travel, not through wormholes or science fiction, but through pure patience and technology. There's a quiet wonder in knowing that some of the galaxies JWST observes may no longer even exist. Their light has travelled for so long that entire stars may have burned out while it was on the way. And yet, here it is, reaching us now, caught on a golden mirror floating in deep space. JWST reminds us that clarity and perspective often come from distance. By looking outward, we learn about the earlier structures, the formation of stars and planets, and perhaps even the conditions for life elsewhere. All of it powered by a telescope so precise, so sensitive, and so elegantly designed that it operates as a kind of interstellar whisper catcher. With every observation, JWST deepens our understanding of the cosmos and our place within it. It's a gentle but astonishing reminder that the universe is not just vast but beautifully connected, and that even in the cold silence of space there are stories waiting to be seen. All it takes is a little golden mirror, a tennis court-sized sun hat, and the courage to look far, far back into the beginning of everything. For centuries, Earth's atmosphere has been both a blessing and a bit of a bother. On the one hand, it keeps us alive, protects us from radiation, and makes for some truly spectacular sunsets. On the other hand, it turns starlight into a jittery mess. Even the clearest skies are filled with tiny ripples of air, each one bending light in unpredictable ways. That's why stars twinkle. It's romantic, sure, but from a telescope's perspective, it's a constant nuisance. And yet, despite this wobbly optical filter wrapped around our planet, astronomers haven't given up. In fact, they've been getting clever, very clever, about how to see clearly from down here on the ground. They've developed tools and techniques that not only fight back against the atmosphere's blurring effects, but in some cases outperform even space telescopes. Two of the biggest breakthroughs in this battle are adaptive optics and interferometry, and they're turning Earth-bound observatories into giants. Let's start with adaptive optics. It sounds like something out of a spy thriller, but it's really a high-tech way of sharpening the view. The basic idea is simple. If the atmosphere is distorting the light coming into your telescope, why not correct it in real time, like putting glasses on the telescope itself? Of course, nothing in astronomy is ever that easy. To correct atmospheric distortion, you first have to measure it, and the atmosphere changes constantly, sometimes hundreds of times per second. That's where laser guide stars come in. Astronomers fire a powerful laser into the sky, creating an artificial star by exciting sodium atoms high up in the atmosphere. This glowing point serves as a reference. By watching how the laser's light wobbles, computers can calculate how the atmosphere is behaving at that moment. Then, using this information, the telescope adjusts a small, flexible mirror, called deformable mirror, many times per second, subtly changing its shape to cancel out the distortions. It's a bit like adjusting a funhouse mirror back into a normal one while the funhouse is still moving. The result? Sharper, clearer images that bring out fine details once hidden in the blur. Thanks to adaptive optics, ground-based telescopes can now rival or even surpass the clarity of space-based ones, at least in certain conditions. We've gone from fuzzy blobs to detailed portraits of stars, planets, and galaxies. And we've done it from observatories here on Earth, without having to launch a single mirror into orbit. But astronomers didn't stop there. If one telescope can produce a good image, what could several working together accomplish? That's the principle behind interferometry, a technique where multiple telescopes are linked together to function as if they were one giant telescope, with a diameter equal to the distance between them. Imagine two telescopes placed far apart. Each one collects light from the same star, but because they're in different locations, the light waves arrive at slightly different times. By carefully measuring these tiny differences and combining the data, astronomers can reconstruct an image with far greater resolution than either telescope could achieve alone. The wider the separation, the finer the details you can see, like turning a pair of binoculars into a planet-sized camera. One of the best-known examples of this is the Very Large Telescope Interferometer, or VLTI, located at the Paranal Observatory in Chile. It uses a group of 4 large telescopes, plus several smaller ones, arranged across a high desert plateau. When working together, they can achieve the resolution of a telescope over 400 feet wide, though they still collect light like individual telescopes. It's a bit like painting a portrait with a tiny brush, but with incredible precision. These techniques have been used to observe stars orbiting the supermassive black hole at the center of our galaxy, to measure the surfaces of distant stars, and to detect the motion of exoplanets around other suns. They're not easy to pull off. The timing and alignment must be incredibly precise, but the payoff is enormous. We're not just seeing light from space anymore, we're decoding it with surgical accuracy. And then there are the giants to come, telescopes that are so large, so complex that they almost sound like science fiction, but they're very real, and construction is already underway. The Extremely Large Telescope, or ELT, being built in Chile by the European Southern Observatory, will have a primary mirror nearly 130 feet across, made of almost 800 individual segments. It will be the largest optical and near-infrared telescope in the world when completed. With adaptive optics built in from the start, the ELT will be able to peer into the atmospheres of exoplanets, study the first galaxies, and test the limits of fundamental physics. Meanwhile, the 30-meter telescope, or TMT, is another upcoming heavyweight. Planned for the summit of Mauna Kea in Hawaii, though its location remains under debate, it will feature a 98-foot wide mirror and an arsenal of adaptive and interferometric technology. Its design is focused on flexibility, allowing it to tackle a wide range of astronomical questions, from the composition of comets to the large-scale structure of the universe. What makes these telescopes so exciting is not just their size, but their precision. Every piece has to work in harmony, every mirror segment aligned just so, every instrument cooled, calibrated, and ready. They're as much feats of engineering as they are scientific instruments, machines built to ask the biggest questions in the universe, one photon at a time. It's a poetic kind of progress. For thousands of years we watched the sky with nothing but our eyes. Then came lenses, mirrors, mountaintops, and eventually spacecraft. But even now, we haven't given up on seeing the stars from here on Earth. We just got smarter about it. With adaptive optics, laser guide stars, and interferometric arrays, astronomers have turned a turbulent atmosphere from a barrier into a puzzle, one that, when solved, reveals a view so sharp it almost seems unreal. And as the new generation of earthbound giants rises, it's clear we're not done yet. We're building telescopes that don't just reach higher, but think faster. They adapt, correct, and combine, all to bring the cosmos into focus. The stars may twinkle, but our vision of the universe is getting steadier, sharper, and more astonishing with every new idea we bolt to the ground and point at the sky. Not all telescopes live on mountaintops or float serenely through the vacuum of space. Some of them live right here among us, in backyards, on balconies, in gardens, or even peeking out from homemade sheds tucked behind garages. These telescopes may not be as large or as powerful as their professional cousins, but they come with something equally important: passion. Amateur astronomy is one of the few sciences where someone with a bit of curiosity, a clear night, and a small telescope can still make meaningful discoveries. The phrase amateur astronomer might sound like someone just dabbling in the stars, but in reality, many of these observers are extraordinarily skilled. They might not have university degrees in astrophysics, but they've got patience, dedication, and hours logged under dark skies. They know the constellations by heart, can recognize the dim glow of a galaxy with a quick glance, and have favorite craters on the moon. There's something timeless about backyard stargazing. It connects us to a human tradition older than writing. Long before anyone knew what a galaxy was, people were charting the sky, watching for meteors, and noticing when a new star appeared that hadn't been there the night before. That tradition continues today, with thousands of amateur astronomers scanning the heavens with telescopes that fit in the trunk of a car or sit snugly on a patio. And they're not just doing it for fun. Many amateur astronomers contribute directly to science in ways that are subtle but significant. One of the most enduring contributions comes from monitoring variable stars that change in brightness over time. These fluctuations can reveal all kinds of things: pulsations within the star, eclipses by orbiting companions, or even the explosion of a dying star. Professional observatories don't have the time or resources to track every single flickering point in the sky, but amateur astronomers do. Through organizations like the American Association of Variable Star Observers, or AAVSEO, they submit brightness measurements that are used by researchers all over the world. Asteroids are another area where backyard eyes make a big impact. New asteroids are discovered regularly, and keeping track of them requires consistent observation. Amateurs help refine the orbits of these objects by taking careful measurements of their positions night after night. In some cases, they're the first to notice when an asteroid passes unusually close to Earth, a comforting reminder that even small telescopes can keep a watchful eye on cosmic traffic. Every now and then, amateurs make the kind of discovery that sends shockwaves through the astronomy community. A previously unknown comet spotted by a hobbyist scanning the early morning sky. A nova, a sudden explosion of brightness from a star that flares up before any professionals have time to notice. These aren't just flukes, they're the result of years of dedication, watching the sky not just casually but with a deep familiarity, the kind of attention that knows when something looks just a little bit off. Technology has helped too. The rise of affordable digital cameras and image processing software has turned many amateurs into highly effective sky surveyors. They can capture detailed photos of planets, galaxies, and nebulae with equipment that fits on a desk. Their images often rival those taken by professionals just a few decades ago. And with online databases and forums, it's easier than ever to share discoveries, compare notes, and collaborate across continents. Citizen science projects have grown from this grassroots enthusiasm. Initiatives like Galaxy Zoo invite the public to help classify galaxies based on their shape, something that, surprisingly, humans still do better than computers. Others let volunteers sift through telescope data looking for exoplanet transits, gravitational lenses, or even the faint signature of distant supernovae. These projects are powered not by billion-dollar budgets, but by curiosity and the collective attention of people who simply enjoy the view. It's not all about discovery either. There's something profoundly calming about stargazing from your own backyard. Setting up a telescope, aligning it just right, waiting for the sky to darken. These are acts of patience and care. You learn to slow down, to adapt to the rhythm of the sky. Watching Saturn's rings drift into view, or tracing the glow of the Andromeda galaxy, is a quiet kind of magic. It's an experience that doesn't demand a PhD or $1 million observatory, just clear skies and a bit of time. Even those without telescopes can get involved. Binoculars are surprisingly effective tools for exploring the night sky. You can see craters on the moon, Jupiter's moons, and even some star clusters with just a steady hand and a bit of guidance. Some observers use only their eyes spotting satellites, tracking the International Space Station, or learning the seasonal dance of the constellations. And then there are the sidewalk astronomers, those generous souls who set up their telescopes in parks and on street corners, inviting passers-by to take a look. With a simple, "Would you like to see the moon?" they open up the universe to people who might never have considered it. These informal outreach moments often leave lasting impressions. After all, It's hard to forget the first time you see Saturn's rings with your own eyes. In many ways, amateur astronomers are the quiet stewards of the sky. They remind us that science isn't always about grant proposals and lab reports. Sometimes, it's just about looking up night after night and noticing the subtle changes. Tracking a star's flicker, measuring a planet's drift, waiting for a comet that may only come once in a lifetime. They keep watch when others are asleep, documenting the sky's behavior with meticulous care. Their contributions may not always make headlines, but they build a foundation of knowledge that supports discoveries of all kinds. They are quite literally part of the universe's ongoing story. So the next time you look up at the stars, know that someone somewhere is doing the same, but with a telescope balanced on a deck or nestled in a field. They're listening to the quiet patterns of the cosmos, not just for themselves, but for all of us. In a world filled with noise and haste, that kind of quiet attention is not just admirable, it's deeply necessary. If you've ever watched the taillights of a car shrink into the distance, you've seen something simple yet profound. Things that are moving away look smaller and fainter. Now imagine that car is a galaxy, and the road is the fabric of space itself stretching out behind it. That's the basic picture behind one of the most surprising discoveries in astronomy, that the universe is expanding, and we wouldn't have figured it out without telescopes. The story starts in the early 20th century, when astronomers were beginning to use large telescopes to study faint, fuzzy patches of light in the sky. Some thought these were just nearby clouds of gas or star clusters within our own Milky Way. Others suspected they were entire galaxies in their own right, vast, distant islands of stars. It was a debate that had astronomers scratching their heads and polishing their lenses. Then came Edwin Hubble and the 100-inch Hooker telescope at Mount Wilson Observatory. In the 1920s, Hubble used this telescope to observe individual stars within these mysterious smudges. By measuring the brightness and behavior of certain types of stars called Cepheid variables, he could estimate their distance, and what he found was staggering. Many of these nebulae weren't part of our galaxy at all. They were galaxies of their own, millions of light years away. That alone would have been enough to make the history books. But Hubble didn't stop there. He also measured how the light from these galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. When light from an object stretches out, its wavelength increases, shifting it toward red. It's the optical equivalent of a siren lowering in pitch as it speeds away. Astronomer Vesto Slipher had noticed redshifts in galaxy spectra before Hubble came along, but it was Hubble who made the connection. The farther away a galaxy is, the faster it appears to be moving away from us. He plotted the data and saw a clear trend. More distance meant more redshift. This relationship became known as Hubble's law. In other words, space itself was expanding. Galaxies weren't flying through space like marbles from an explosion. They were being carried apart by the stretching of space itself. The implications were enormous. If everything is moving apart now, then in the past it must have all been much closer together. That led to the idea of a cosmic beginning, the Big Bang. But the expanding universe doesn't mean we're at the center of it all. It means that space is stretching everywhere, equally. No matter where you stand, on Earth, in another galaxy, or on an imaginary planet orbiting a lonely star in deep space, you'd see other galaxies moving away from you. It's a bit like raisins in a loaf of rising bread. As the dough expands, every raisin gets farther from every other one, but no single raisin is the center of the action. This concept reshaped our understanding of the cosmos. Telescopes were no longer just tools for mapping stars, they were time machines, revealing a universe that wasn't static or eternal, but changing, evolving, growing. And it wasn't just about galaxies getting farther apart, something deeper was at play. As astronomers studied more galaxies and measured their redshifts, they discovered something curious. Not only was the universe expanding, but the rate of expansion appeared to be accelerating. That was completely unexpected. Gravity, you'd think, should be slowing everything down, pulling galaxies back toward one another. Instead, they were speeding up, as if being pushed by some invisible force. That mysterious force was eventually given a name: dark energy. We don't yet know exactly what it is, but it seems to make up roughly 70% of the universe. and we only noticed it because of careful telescope measurements, tracking the behavior of distant supernovae, exploding stars whose brightness tells us how far away they are and how fast the universe was expanding when their light began its journey. All of this pointed to something fascinating. The universe had a beginning, it's expanding, and it may go on expanding forever. But what about the very start? What happened at time zero? To answer that, scientists turned their attention to the leftover light from the Big Bang itself. In the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were working with a large antenna in New Jersey when they stumbled upon a strange, persistent noise. No matter where they pointed the instrument, they heard the same faint hiss. At first, they thought it might be interference from a nearby city, or maybe pigeons nesting in the antenna. But after some cleaning and head-scratching, they realized they had found something extraordinary. That faint signal was the cosmic microwave background radiation, light from the early universe, stretched by billions of years of expansion until it now appears as low-energy microwaves. It's the afterglow of the Big Bang, a thermal echo from when the universe was just a few 100,000 years old and had cooled enough for light to travel freely. Since then, satellites like COBE, WMAP and Planck have mapped this radiation in incredible detail, revealing tiny fluctuations in temperature, ripples that would eventually become galaxies, stars and planets. These subtle patterns also give us clues about what happened in the very first moments of the universe's existence. One of the key ideas to come out of this research is called cosmic inflation. According to this theory, in the first tiny fraction of a second after the Big Bang, the universe underwent a brief but unimaginably rapid expansion, growing from smaller than an atom to larger than a galaxy in less than the blink of an eye. Inflation helps explain why the universe looks so uniform in all directions, and why the cosmic microwave background is so smooth with only tiny fluctuations. It's a concept that stretches the imagination and space itself, and yet we've arrived at it not through philosophical pondering, but through careful measurements made by telescopes on mountaintops, in balloons, on satellites and across the globe. These instruments don't just collect light, they collect time. They give us a record of how the universe has changed, and they hint at what it might become. From the first glimpse of distant galaxies in fuzzy black and white images to the crisp redshift data of modern observatories, telescopes have taught us that the universe isn't a static backdrop. It's a living, stretching, glowing thing, always in motion, always revealing more, and perhaps the most humbling discovery of all, that the more we look outward, the more we find our place within this vast, expanding story. Small, yes, but part of something truly enormous and endlessly unfolding. Telescopes have come a long way since Galileo squinted through a tube and spotted the moons of Jupiter. We've built them bigger, smarter, and colder. We've put them on mountains, launched them into space, and even taught them how to correct their own vision. But astronomy, much like the universe it studies, never stops expanding. The question is, what comes next? It turns out the future of seeing far is full of bold ideas and seriously impressive acronyms. One of the most exciting projects on the horizon is the Nancy Grace Roman Space Telescope. Scheduled to launch in the mid-2020s, it's often described as Hubble's wide-eyed cousin. Where Hubble has a narrow field of view, Roman will be able to survey vast portions of the sky with incredible detail. Think of it as switching from a magnifying glass to a wide-angle lens without losing sharpness. Roman is designed to tackle big questions, literally. It will help map the structure of the universe, hunt for exoplanets, using a technique called gravitational microlensing, and probe the mysterious nature of dark energy, the force that seems to be accelerating cosmic expansion. Its wide field of view means it can capture millions of galaxies in a single shot, offering a kind of cosmic census that could reshape our understanding of how everything is arranged. But if Roman is the next big leap, Le Voir is the next cosmic vault. The large UV optical IR surveyor, Le Voir for short, is still in the concept stage, but it's already aiming for the stars. Picture a telescope even larger than the James Webb, with a mirror up to 50 feet across. That would make it the largest space telescope ever imagined. LUVOIR would be capable of directly imaging Earth-like exoplanets and analysing their atmospheres for signs of life, oxygen, water vapour, maybe even something a little more exotic. What makes LUVOIR especially ambitious is its potential to do many things at once. It would be a Swiss Army knife of space telescopes, able to switch from studying the birth of galaxies to peeking at a star system just a few dozen light years away. If it's built, and it's a very big if, LUVOIR could be the telescope that finally helps answer the age-old question, are we alone? But building a telescope that large comes with some tricky engineering problems. For one, it would probably need to be assembled in space, possibly by robotic arms, or even astronauts aboard a future space station. That's not something we've ever done on this scale before, but the idea is becoming less science fiction and more blueprint with every passing year. Meanwhile, other projects are reaching even further, into both space and quantum physics. One area of intense interest is quantum-enhanced imaging. Quantum sensors could detect photons more precisely, reduce noise in faint signals, and even allow for imaging objects that are traditionally considered invisible. These ideas are still very much in the experimental stage, but they hint at a future where we're not just using bigger mirrors, but smarter physics. There's also growing interest in building observatories far from Earth, not just in orbit, but on the Moon. The Moon's far side is one of the quietest radio environments in the solar system, shielded from Earth's constant chatter. It could be an ideal spot for a low-frequency radio telescope, one that could listen to signals from the cosmic dark ages, the period before the first stars lit up the universe. A telescope on the Moon could also be more stable than one floating in space. No atmosphere, no weather, and almost no tectonic activity means instruments could remain motionless for years or decades. Of course, there's the small matter of getting there and building it, but the Artemis program and private spaceflight are making lunar infrastructure feel a bit more plausible than it did just a decade ago. Then there's the idea of placing telescopes in truly deep space, well beyond Earth orbit, beyond the Moon, maybe even at stable gravitational points like Lagrange points 4 and 5. Some proposals imagine sending telescopes far enough away that they could use the Sun itself as a gravitational lens. That's right, using the Sun's gravity to bend and magnify light from distant objects, just as Einstein's theory predicted. It's a bold idea that could, in theory, allow us to image the surface of an exoplanet in another solar system. Naturally, these projects come with enormous logistical and financial challenges. The farther we send our telescopes, the harder they are to maintain. We can't exactly send a repair crew 1 billion miles out to tighten a bolt. But the payoff could be extraordinary. Images and data so detailed that they make today's deep field pictures look like Polaroids. As we look to the future, there's also a shift in how we think about telescopes, not just as tools for astronomers, but as collaborative instruments that anyone can learn from. More and more data is being made public. Citizen science projects are flourishing, and artificial intelligence is helping sift through vast amounts of information. The future of telescopes may not just belong to scientists in lab coats, but to curious minds around the world, connected by the web and driven by wonder. One thing is clear, we are far from finished. Every time we build a better telescope, we end up with new questions. Every new image reveals things we didn't expect to see, and every glimpse of the distant universe reminds us just how much is left to explore. So how far is too far? That's not a question astronomy is ready to answer. As long as there are stars forming, galaxies colliding, and light traveling across the cosmic sea, we'll keep finding ways to follow it. Whether from a cold crater on the Moon, a distant satellite in deep space, or a smart little telescope in someone's backyard, the eyes of humanity are getting sharper, and as long as there are photons making their ancient journey through the dark, we'll be here, building mirrors, stretching wavelengths, and pointing our instruments upward, always looking, always listening, always wondering what waits just a little bit further away. As we come to the end of this long starlit journey, it's worth taking a quiet moment to reflect, not just on what telescopes have shown us, but on what they represent. These aren't just instruments of glass and metal perched on mountaintops or floating through the dark. They are extensions of our longing to know. They are the eyes we built when our own vision fell short. Gentle watchers of the sky, patiently collecting stories written in starlight. Every telescope, no matter how small, is a symbol of curiosity, of the soft, persistent question we've been asking for millennia. What's out there? And not just what, but how, why, and perhaps, most quietly, what does it mean for us? These instruments don't answer all our questions, far from it, but they illuminate the path forward. Each new discovery becomes the next stepping stone. And just as important as the technology is the patience behind it. Telescopes are patient creatures. They wait for the skies to clear, for a planet to pass in front of a star, for a photon that has travelled billions of years to reach a mirror polished with care. In a world often shaped by speed and noise, astronomy asks us to slow down, to breathe, and to look a little longer. The universe moves at its own pace, so must we, if we wish to see it clearly. Perspective, too, is part of what makes telescopes so quietly powerful. They remind us that we are small, but not insignificant, that our world, warm and full of colour, orbits an average star in an average corner of one galaxy among billions. But that smallness is not a flaw. It's a feature of the story we're in. A telescope shows us the vastness not to diminish us, but to invite us into it, to let us marvel, to feel that odd, wonderful combination of humility and connection that only a truly star-filled sky can offer. And the sky is still full of light we haven't met yet. There are stars that haven't risen in our view, galaxies whose light hasn't yet reached us, phenomena we haven't even imagined. Somewhere out there, in the soft darkness between the stars, are answers to questions we haven't thought to ask. Every photon we catch is a message in a bottle, floating across cosmic oceans, waiting for someone, maybe even you, to open it. Even now, while you rest, a telescope is watching. Somewhere, a dish is listening. A mirror is capturing ancient light, and someone is looking upward with wonder. The universe doesn't sleep, but it dreams. And through our telescopes, we get to share in those dreams. It's comforting, isn't it? To know that we've built quiet machines whose only job is to gaze upward, to be still, to notice. They don't rush, they don't judge, they just wait for light and welcome it in. And maybe, in our own way, we're doing the same. As you lie there, drifting towards sleep, maybe your thoughts are wandering too, toward moons and nebulas, toward distant galaxies, and the idea that somewhere out there, someone else might be wandering too, that maybe all of us, in our own ways, are watching the sky. Thank you for spending this time here tonight. If you found a little peace, a little wonder, or even just a little space to breathe, I'm grateful. If you enjoyed this journey and haven't already, I gently ask you to leave a like, or subscribe to this channel. It helps more sleepy explorers find their way here. And if you're still awake, I'd love to know, where are you listening from tonight? What time is it where you are? Whether it's the early hours before dawn or the quiet lull after sunset, I hope you've found some stillness here, some comfort in the stars, some joy in the knowing that the sky above us is not just beautiful, but alive with stories. We'll never see it all, but we keep watching. And that, in its own quiet way, is enough. Sleep well, gentle dreamer. The universe will keep watch.